Hello, and welcome to Differential Equations. This is Lecture 17, Undamped Vibrations. Last time, we talked about how the Laplace transform turns constant coefficient linear ODEs into algebra. So solving them just becomes a matter of doing some algebra and then recognizing the solution you get. This time, we're going to talk about vibrations in mechanical systems. Okay, so when a physical system in stable equilibrium is disturbed, we expect vibrations to occur as it is subject to forces working to restore its equilibrium. When modeling these systems, Newton's second law of motion, F equals ma, leads to second order differential equations. Since acceleration is the second derivative of position, right? A is x double prime. As a stereotypical example, let's consider a cart of mass m attached to a nearby wall by means of a spring. Right, so suppose we have, here's a wall, and then over here we have our cart, mass m, right, and right above, or right below the center of mass, let's measure a displacement from rest. So this is how much the position has moved. And here let's suppose that it's attached to a wall by the spring. Okay, so the spring would exert no force when we're in equilibrium. So but if the cart is moved away from equilibrium, then Hooke's law, right, Hooke's law, named after the 17th century brilliant British scientist and rival of Newton, Robert Hooke, states that within the relevant elastic limits, so as long as you don't pull the string too far or compress it too much, the force needed to extend or compress the spring by some distance x scales linearly with x. Right? Thus, in our example, the spring exerts a restoring force, let's say F sub s for spring, of minus k times x, where k is a constant, positive constant, measuring the stiffness of the spring. And Newton's law takes the form, so mass times acceleration is equal to the force minus kx, right? Or we can rewrite this as mx double prime plus k times x equals 0, or since we prefer to have the coefficient of the highest derivative be equal to 1, x double prime plus k over m x equals 0. Okay, so this is a second order linear equation with constant coefficients, and it's easy to write down the solution. Right, the general solution is x of t is equal to a times cosine of square root k over m times t plus b sine of square root of k over m times t. Okay, so as expected, in the absence of damping, the solutions oscillate periodically. With natural frequency, omega naught equal to the square root of k over m. Okay, so for example, if the cart is pulled aside, the position x equals x naught, and then released without any initial velocity, at time t0, and our initial conditions are x of c at time 0 is x naught, and velocity at time 0, just say the derivative of x with respect to t at time 0 is equal to 0. So then it's easy to solve here for the constants, and we get a is equal to x naught, b equals 0. So the solution becomes x of t is equal to x naught times cosine of omega naught times t. Right, with omega naught the natural frequency. Oh. Okay, let's stare at this and name some of the terms. So here the amplitude of this simple harmonic vibration is x naught. Its period, right, capital T, right? So the period is the time required for one complete cycle. Is, okay, we're just staring at this. This is periodic function. Cosine has period 2 pi. So cosine of omega naught times t is going to have period 2 pi divided by omega naught, right? Which would be 2 pi times the square root of m divided by k. Its frequency, call it f, right? Which is the number of cycles per unit time. Is 1 over t, right? So 1 over 2 pi times the square root of k over m. Okay, and note that the frequency of the vibration increases, if the stiffness of the spring increases, or if the mass of the cart is decreased. Just as our common sense would lead us to predict. Okay, so there we were just considering what happened with these initial conditions. So now instead, let's consider adding an external force. So the equation would become m times the acceleration is equal to minus kx plus f of t. So often, it makes sense to assume that the forcing term is some periodic function. For example, for an automobile suspension, one source of forcing is the rotation of the wheels. Which is periodic. Okay, so let's pick a very simple periodic function. And let's consider the equation mx double prime is equal to minus kx plus sine of omega t. So here omega is not necessarily the same as omega naught, the natural frequency. It's just some omega. And we can rewrite this equation as x double prime plus k divided by m times x is equal to 1 over m sine of omega t. Okay, so this is a linear equation with constant coefficients, but non-homogeneous. So we know a lot about solving these equations now. What we need is a particular solution. With this right-hand side, undetermined coefficients is the way to go. So let's try xp of t equals little a cosine omega t plus little b sine of omega t. Right, if we plug this in, right, the right-hand side, xp double prime plus k over m xp would become, okay, well, If you take two derivatives of cosine, you get minus cosine. If you take two derivatives cosine omega t, you're going to get minus omega squared cosine omega t. And similarly with sine, two derivatives of sine omega t is going to give us minus omega squared sine omega t. So taking two derivatives of xp is just going to give us minus omega squared times xp. And then we have plus k over mxp. Right, so that's k over m minus omega squared times xp. And then we want this to be equal to 1 over m sine of omega t. Right, so as long as k over m minus omega squared is not equal to 0, right, which is to say omega is not equal to square root of k over m, which is omega naught, one particular solution is xp of t equal to 1 over m sine omega t divided by k over m minus omega squared, right, which we can rewrite as sine omega t divided by k minus m omega squared. Okay. Hence the general solution to mx double prime equals minus kx plus sine omega t, right? Assuming omega is different from omega naught, right? Square root of k over m. Is x of t equals some constant times cosine omega naught t plus some constant times sine omega naught t, right? So the general solution of the homogeneous equation plus our particular solution, sine of omega t divided by k minus m omega squared. Okay, so let's think some more about this particular solution. Xp of t equals sine omega t divided by k minus m omega squared. Okay, so first notice that this has positive amplitude. For omega squared small. So it's reinforcing the vibrations that we had going on. So we say that it is in phase with the driver. The particular solution has negative amplitude for omega squared large, right? So in this case, it's counteracting the natural vibrations. So we say that it is pi out of phase with the driver. When the driving frequency omega is close to right? The natural frequency omega naught, then the amplitude becomes very large. Okay, and if you were to plug in omega equals omega naught, right? Well, you're not allowed to plug that in for a couple of reasons. One of them is that we only worked out what the general solution was under the assumption that omega was not equal to omega naught. Another more important reason is that, of course, if you plug that in, then the bottom becomes 0, and you're not allowed to divide by 0. So let's just say that the amplitude is undefined when omega is equal to plus or minus omega naught. Right, so when their squares are the same. So this last case is a phenomenon called resonance. Okay? Generally speaking, we use the word resonance when the vibration of one object causes another object to vibrate at higher amplitude. Right? Resonance can be good. Right? So for example, if you're designing a concert hall or you're building musical instrument, you're constructing a musical instrument, then there are some sort of resonances you're looking for, or it can be bad, catastrophically bad, like if you're constructing a bridge or a building. If you've never seen the videos of the Tacoma Bridge, you should definitely look those up. Okay, but in any case, resonance is a very interesting phenomenon that you want to study and understand because you either want to promote it or avoid it. Of course, if omega is equal to omega naught, then the particular solution we found above doesn't work. Right, and well, undetermined coefficients, we know what to look for. To find a particular solution, we would look for one of the form xp of t is little a times t cosine omega naught t plus b times t sine omega naught t. Right? And you can check that xp of t equals minus t cosine omega naught t divided by 2m omega naught. Works. Okay, we'll stop there and next time talk about what happens when you introduce damping.